Hello, this is the sixth video of the first order differential equations series for OCR Pure Core Further Mathematics, and it looks at finding integrating factors. When dealing with first order linear differential equations of the form dy by dx plus p of y equal q, where p and q are functions of x, if the left-hand side is not a perfect derivative of a product, then we can make it so by multiplying by a function of x called an integrating factor, and we saw this in the previous video. So we need to find a function f of x such that f of x dy by dx plus f of x times p of x y equals d by dx of y f of x. In other words, a perfect derivative of y f of x. It can be shown that this function f of x is the exponential of the integral of the function p of x integrated with respect to x, which is the required integrating factor. For a proof of this result, please see your textbook or online. It's also worth noting that when we look at this integral of p dx, we will not need a constant of integration. If you try using one, you will find it becomes a multiplier that's eliminated, and thus it may safely be ignored. One of the rare occasions when the plus c can be left out. Again, a full explanation of this may be found in your textbook. If we look at this example, we can identify that the function p of x equals 1 over x. Then, looking for our integrating factor, f of x will equal the exponential of the integral 1 over x dx, or the exponential of the natural log of x, which is simply x. Multiplying through by this, we would have x dy by dx plus x over x, which would therefore cancel out, times y, equals 4x cubed. This is the perfect derivative of xy. And therefore xy will equal the integral of 4x cubed, which will be x to the 4 plus c. If we then divide through by x, this leads us to the general solution, y equals x cubed plus c over x. In the second example, it's not quite in the right form yet. We need to divide through by cos x. This would give us dy by dx plus 2 tan x times y equal to cos squared x. Now that it is in the correct form, we can see that p of x equals 2 tan x, and q of x is cos squared x. But in terms of working out the integrating factor, what we are interested in is the exponential of that 2 tan x dx, or e to the 2 natural log of sec x. We can write that as e to the natural log of sec squared x, and thus equal to sec squared x. Thus sec squared x is our integrating factor, and when we multiply through by that, we would have sec squared x dy by dx plus 2 tan x sec squared x times y equals cos squared x times sec squared x. I'm going to write that as 1 because we know that cos x equals the reciprocal of sec x and vice versa. So the left-hand side is the perfect derivative of sec squared x times y. Thus, when we integrate, sec squared x times y will equal the integral of 1 dx, or x plus c. And then when we divide through by sec squared x to isolate the y, we get the result that y equals x plus c cos squared x, again remembering that cos x and sec x are reciprocals. In summary then, to find an integrating factor for the type of equation where dy by dx plus py equals q, p and q both being functions of x, the required integrating factor f of x is found by the exponential of the integral p of x dx. So multiplying through by f of x gives us f of x dy by dx plus f of x py equals f of x q. And the left-hand side is the perfect derivative of y f of x. Thus integrating with respect to x gives us y f of x equals the integral f of x q of x dx.